Hiya! So in this video, we're going to talk about eigenvalues and eigenvectors of linear operators. And in essence, so this is going to, so I kind of mentioned Italian German last time. And the joke was that actually the word eigen is a German word meaning like its own self, like your own proper self thing. So it's like an internal, intrinsic something. So we're going to talk about eigenvalues and eigenvectors of a linear operator in essence. In other words, it's going to be like how we kind of thought about like the determinant or the trace last time, right? How it was somehow this value was intrinsic to the operator itself and it didn't depend on the matrix. This eigenvector and the value is going to be a very similar idea. So what is the eigenvalue, the eigenvector? So an eigenvector is going to be some vector of a linear operator P. So we have a linear operator P. An eigenvector of P is going to be a vector such that P of X is just lambda of X, right? So why are we doing this lambda of X? Think of this as, so it's just some scalar multiple of itself. So lambda here is a real number. Lambda is a real number. And lambda we actually call the eigenvalue, right? So X is the vector, lambda is the value. Eigenvector, eigenvalue. So P scales X by lambda. So it just kind of keeps it to itself. It keeps this vector to itself where it just scales it. So when lambda is equal to 1, basically think of what happens if lambda is equal to 1. So if lambda equals to 1, P of X is basically keeping X itself. It keeps the vector as itself. It doesn't change the vector. So these eigenvectors are completely fixed by the action of P. And these will be useful later on in subsection 1.6.2, when we start talking about rotations in three-dimensional Euclidean space. So this is something we'll use later on. But it's just the kind of thing to think about when lambda is equal to 1. We're basically just keeping the vector as is. And so what we're going to do is this following lemma. We're basically showing that every eigenvector gives rise to some one-dimensional line of eigenvectors. Yeah. I want to say this should say eigenvalue. No, okay. Yeah, eigenvector. No, that's okay. So let's actually see this lemma, what it's saying. So we start off with P as a linear operator on a vector space V. And X is going to be some eigenvector with lambda its eigenvalue. So X is eigenvector, lambda is the eigenvalue, P is a linear operator, V is the vector space. Then every vector in the span of X, so remember span of X is just taking the linear combinations of X, right? Then they're also all going to be eigenvectors with eigenvalue lambda. So the key part are also eigenvectors with eigenvalue lambda. So in other words, like I was saying before, that every eigenvector, in this case X, gives rise to a one-dimensional line of eigenvectors. So all of these eigenvectors are associated in the span of X. And they have the same eigenvalue, which is kind of cool. So all of these vectors in this line get scaled by the same proportion. And this is not too hard to see. This is just using kind of some of the previous things, where we know y is in the span of X, and so we can write it as some multiple of X. And then using the linearity of P, right? So this is just by definition. This is linearity. This is by definition that X is an eigenvector. So eigenvector, vec, this gives us this. Oh, no, sorry. This gives us this first one. This is linearity. And then this, again, is just this part. So P of y is just lambda of y. And that's it. Super simple, super nice, easy. So there's a lot of history and work that gets done in eigenvectors and eigenvalues. That's all we're gonna need for our case. I don't really study eigenvalues, eigenvectors, but there is a lot of people that do look at these and like the spaces they kind of form and stuff like this. So there is a lot of like awesome things you can do with these things. I don't really look at them though. So we'll kind of brush those aside for now. So since the last few videos were longer, we're gonna break this video up in two, even though they're both gonna be fairly short. I'd rather have shorter videos than longer videos. So we'll cut this here, and in the next video we'll do some examples, or we'll do an example. So I will see you then for this example. Peace.